Hello guys, good morning. Good morning to all of you. Am I audible? Am I visible? Is everything all right? Let me know quickly, then we'll start. Today we are starting a new chapter called radioactivity. From radioactivity, various questions came previously, and there is a high chance that you will get a question from radioactivity. Ajay, good morning. Where is Harry today? Okay, Harry is also here. Let's start this radioactivity chapter. It's a very easy topic actually. You have already studied this topic in class 12. So in this section also we'll not be doing much more than that. Basically class 12 level thing and a few extra thing is there. So in brief, it is a very easy topic. So let's start with this. Radioactivity is the phenomena where certain heavy atomic nuclei, typically with neutron to proton ratio 1.5, greater than 1.5. So this ratio must be greater than 1.5, then those heavy atomic nuclei will exhibit this radioactivity phenomena. So you see, number of neutron is more than number of proton by 1.5 times, like uranium, thorium, radium, etc. spontaneously disintegrate. This disintegration is accompanied by the emission of either corpuscular, such as alpha particle, beta particle. It's a corpuscular, particle-like radiation, or electromagnetic radiation such as gamma rays. So alpha decay and beta decay, these are corpuscular radiation, and electromagnetic radiation such as gamma rays, this is non-corpuscular. Now certain fundamental aspect of radioactivity is that it occurs at a constant rate. This is a very important thing, that radioactivity occurs at a constant rate. It keep on going over time, and it is unaffected by external physical or chemical conditions such as temperature. If you increase or decrease the temperature, there will be no effect on the radioactivity. It will continue to disintegrate at a constant rate. If you apply high pressure, low pressure, it doesn't matter, the radioactivity will not be changed, or any other influences to which the atom may be subjected. Radioactivity is an intrinsic nuclear property of the element. During radioactive decay, nucleus of the atom undergoes transmutation, means it will completely, the original element will be completely transformed into a new element, entirely new element with different atomic nucleus. So this one you must keep in mind. After the decay, the original element, this is also called parent nuclei. Okay, original nuclei is known as parent nuclei, and the product, that is called as daughter nuclei. Daughter nuclei. So parent nuclei is converted into daughter nuclei, some completely new nuclei is formed. It's an intrinsic nuclear property. Now these are basic fundamental thing. I have attached some images to understand it more clearly. As you can see, this nucleus of an atom consists of protons and neutrons, in short nucleons, and let's say if this is proton and this is neutron, if these are, let's say, proton and these are neutron, and as you can see in alpha particle it consists of 2 protons and 2 neutrons. Okay? 2 protons and 2 neutrons. Gamma radiation, highly energetic electromagnetic photon, so this is not corpuscular, and high energetic electron, beta radiation. These are the basically 3 radioactive decay. After completing this radioactivity phenomena, we will be going for the different particle radiation and the electromagnetic radiation, alpha, beta and gamma decay separately. Now what is the nature of these 3 kind of radiation? So you know, alpha particle is a positive type of radiation, positively charged, positive type of radiation is like positively charged. Beta radiation is negatively charged, beta minus actually, and this gamma radiation is neutral. So depending on that, they will be deflected if you keep a radioactive substance which emits all this kind of nuclear radiation such as alpha, beta and gamma, and as you can see the magnetic field is cross means into the page. Okay, it is, if you consider a page, cross symbol is given means the magnetic field is going inward. If there is a dot, you will understand the magnetic field is coming out of the page. Okay, here dot cross means magnetic field is going into the page. So if you keep a radioactive sample here, then the radiation is moving perpendicular. Alpha is moving perpendicular to the magnetic field, beta, gamma, all of them are moving perpendicular in a perpendicular direction. And as you can see, gamma ray being neutral is undeflected, alpha ray is moving into some direction, and beta wave is moving into other direction. So it shows the opposite polarity, opposite charge of these 2 radiation. And as you can see, from this figure it is clear that alpha is positively charged, beta is negatively charged and gamma is neutral. And their penetration power is also shown here. You see, alpha particle can penetrate cannot even penetrate a paper. Beta radiation can penetrate a paper, but it can be stopped by an aluminum foil. Gamma is highly penetrating radiation, so this is most dangerous. It can penetrate through paper very easily. In fact, it penetrates through aluminum very easily, and through lead also it can penetrate, but most of it gets attenuated. Okay, so that is why whenever we have radioactive sample, it is preserved in a lead box. Now let's slowly go into the main discussion, law of radioactive decay. So you must have seen the radioactive disintegration phenomena. It is exponential nature. The atomic nuclei disintegrate exponentially because it goes like this. So to happen the complete decay, how much time ideally requires? It is infinity, right? So whenever you consider an exponential curve, so you see it goes like this. It doesn't touch the x-axis. It is supposed to touch the x-axis at infinity. So if the nuclear radiation is following this pattern, so we can theoretically say that it will take infinitely long time to complete the decay process. So you see, the decay of a radioactive substance is a random process. That is, the time at which one nucleus will decay is independent of the decay of all other nuclei and cannot be predicted. Let's say you have an uranium sample, 92 uranium. So in the sample there will be many nuclei. Sample consists of atoms. Let's say we are considering the nucleus. So many nuclei are there. So it is not like all the uranium nucleus will decay at one time. It's a random process. Okay, let's say there are 8 number of nucleus. So in the half lifetime we'll define later. Half lifetime means when the sample nuclei becomes half. So here 8 is there. So after one half life, there will remain 4 nuclei, but it is a random process. You do not know which 4 nuclei will decay first. Every time it is decaying, but you never know out of these 8 nuclei which nuclei is going to decay, whether this is this nuclei or this nuclei or this nuclei or this nuclei, but the probability is same, right? They are all identical, so probability for decay of them are same. But it is a random process. That is, the time at which one nucleus will decay is independent of the decay of all other nuclei and cannot be predicted. You cannot predict exactly when a given unstable nucleus will decay. However, proportion of nuclei decaying in a certain time can be predicted very easily. So after certain interval, let's say 3 to 4 nuclei decays, so this can be told. You cannot say that which nuclei will decay, but you can say how much proportion will get decay. This probability is called the decay constant. Understood? Decay constant. So decay constant basically gives you a measure like what proportion of nuclei will decay at a certain time. It determines the rate at which the material will decay. So the more high value of decay constant means heavy decay. Okay. Now disintegration rate of a radioactivity substance at any time t is proportional to the number of radioactive nuclei present at that instant. That is, those nuclei that have not yet been decayed. So let's say we have inside the substance there may be hundreds and thousands and more than that, millions, it can be millions also, number of nuclei. Let's say for our example, let's say 100 nuclei are there. So disintegration rate will depend like how much radioactive nuclei present at that instant. So if I consider that let nt, t is the time, n is the number of nuclei or nuclei, nt be the number of active nucleides present in the sample at any time, let's say t. Then experimentally this result has been obtained. Then we have experimentally look, dn by dt, dnt by dt, it is proportional to the number of nucleides present. As you can see, as the number of nucleides getting decayed, so n value is decreasing, right? Number of nuclei present in the sample is decreasing. So dnt by dt, time is always positive. If you start at 10 am, then the decay, let's say 10:05 am, 10:10 am. So time is moving in the forward direction. So change in time is positive. dnt, this is negative, but this is positive. So that is why a negative sign is used. Understood the significance of negative time? dt is positive, dnt is negative, and the resultant on the right hand side, it should be same, na? So nt is positive, so if you want to make it positive, you have to multiply with a negative sign. And from this we write dnt by dt. This proportionality constant is called the decay constant, minus lambda nt. This minus we have taken. So this is a very important formula. dn by dt is equals to minus lambda n. Now a decay constant is a characteristic of the particular nuclide. A characteristic constant of the element. So it will be different for uranium and radium and thorium. So depending on the nuclide, it will be different. The negative sign signifies that nt decreases with time. Okay. So we can make use of this equation. dnt by dt is equals to minus lambda nt. So from this we can write dnt by nt is equals to minus lambda dt. We can now take the integration on both sides and you will get ln nt equals to minus lambda t plus some constant, let's say a. A is the constant of integration. Now whenever we consider a substance, so it will composed of a certain number of nuclides. Initially a certain number of nuclides will be there if you consider a substance. So let's say initially at t equals to 0 there are n0 number of nuclides present. Okay, so we can make use of this initial condition. At t equals to 0, number of nuclides present at the sample or substance is equals to n0. The initial number of nuclides, and hence you see if you put t equals to 0, So A is equals to ln n0. Therefore, ln nt is equals to minus lambda t plus ln n0. So what kind of graph you can expect? Let's say if you plot here ln nt versus t, if you plot, so ln nt, it is basically y equals to mx plus c formula, so straight line. So it will cut at ln n0 at the positive x, so the slope is negative. It will be something like this. It will cut at ln n0. Is that okay? Now this relation can also be written as ln nt by n0 is equals to minus lambda t, and this relation can be finally written as nt is equals to n0 e to the power minus lambda. This is known as radioactive decay law. This is the most important formula. This is known as the radioactive decay law. So this is the law of radioactive decay. So radioactive decay happens exponentially. Now if you look at this curve, few observations you can make. What are the observations from this equation? So the curve will draw. First of all, you see, when t is equals to infinity, then what is nt? Nt is equals to n0 to the power minus infinity, so it is 0. It means the radioactive substance will decay completely only after infinitely long time. Okay. Another thing, or another observations we can make. Let's say, let's name this observation number 2. If you substitute t is equals to 1 upon lambda. What is lambda? Decay constant. So reciprocal of the decay constant. So nt will be, if you put t equal 1 by lambda, so it is e to the power -1. So n naught by e. So we can also define the lambda from here. So the time requires for the substance to decay 1 by e times of its original number is the decay constant, you can say. That is, so from here also you can quantitatively define the decay constant, the disintegration constant or decay constant. Disintegration constant lambda is defined as the reciprocal of the time t during which the number of undecayed radioactive substance, number of undecayed radioactive nuclei is left number. What is nt? Nt is the number of nuclei present at that moment, at time t. So that is the undecayed, which is remaining in the at the substance. Those are undecayed, na? We are not keeping track of the decayed. We are keeping track of the how much is left. So which the time during which the number of undecayed radioactive nuclei left is equal to 1 by e times their original amount or number. Okay, now let us go for a definition called half-life. Only exponential term remains in nt. No, for a particular time t, nt becomes n naught n0 by e. Here in this is the original expression. If you put t is equals to 1 by lambda, then it becomes e to the power minus lambda by lambda, so e to the power minus 1. So this e is coming in the denominator, so n0 by e. No, this is at a particular time. Overall, the behavior is described by this equation. Clear, Harry? Now what is half-life? Half-life is the time by which the number of radioactive nuclei becomes half of their original number. The half-life of a radioactive nuclei is defined as the time t half, is denoted by t subscript half, in which the original number of radioactive atoms is reduced to half by the way of disintegration. You see, if you put T is equals to T half, what do you see? Nt will become N0 e to the power minus lambda T. T is T half, right? Now what is Nt? At T equals to T half, Nt is half of its value. So originally it was N0, so it will be half, so N0 by 2. So from here we can see that e to the power lambda T half is equals to 2, that is T half is equals to ln2 by lambda. ln2 is 2.303 times log 2 divided by lambda, and this value has the value 0.693 divided by lambda. The value of ln2 is 0.693. So generally you will remember this formula: T half is equals to 0.693 divided by lambda. So this is the ultimate formula you need to keep in mind, and this will be used many times. So we can also write another relation, lambda into T half, the product of it. It is 0.693, that is constant. The product of the decay constant and the half-life is a constant for all the active nuclei presence. Is it done? Now let us try to understand all these things from a graph. Graph is the best way to understand all the physical processes. So as I have already mentioned that the radioactive decay will look like, so you see, if I plot, let's say NT here, NT versus T, so it will follow this relation NT is equals to n0 e to the power minus lambda. Initially, how many nucleides are present? N0. You put t equals to 0, you get nt is equals to n0. So let's say this is your n0. So it will start from here, and it will exponentially decay. So it will decay exponentially. It will not touch this t axis, but it will exponentially decay. Okay, it should have been more steeper. Let's try to do it. So approximately this is the curve. Here along this we are putting n0. So this is n0. So after one half life, if you put t equals to t half, you know nt becomes n0 by 2. So n0, if this is n0, this will be your n0 by 2. Isn't it? So this will be your n0 by 2, and the time taken will be t half. Now after another half life, this original amount, after one half life, the amount becomes n0 by 2. In the next half life, n0 by 2 will be halved. n0 by 2 will be n0 by 4. So this will be 2t half. So this will be your n0 by 4. Again half of it. So after the third half life, what will it become? n0 by 8, and it will keep on going. So this is 0, this is your t half, this is your 2t half, and if I say this is your t times t half, and so on. So as you can see, after one half life, it is remaining half of it. After two half life, it is remaining 1 by 2 square. You can say, you just try to understand the pattern. One half life, after one half life, let's say nt. What is nt? It is n0 by 2. After two half lives, nt is equals to n0 by 2 square. After three half lives, nt is n0 by 2 cube. In this way, if you go and if you say that after n half lives, nt will become n0 by 2 to the power n. Okay. So if you want to calculate the fraction, this is nt. So the ultimate formula here is equals to Nt is equals to n0 by 2 to the power n, where n is the number of half-lives. So how can you understand how many number of half-lives are there? Let's say if t time has elapsed, then what will be the number of half-lives? Can you tell me? N is equals to t time has been elapsed, or 1 half life is t half. So t by t half, if you do, that will give you the number of half lives. Okay, let's say if I say that the half life of a nucleus is 1 hour, sorry, let's say 2 hours. So if 10 hours is passed, how many half lives have passed or elapsed? If I say that the half life of a nuclide is 2 hours, if the elapsed time is 10 hours, how many half lives it has undergone? Tell me quickly. If the half life of a nuclide is 2 hours, and if I say that 10 hours has passed, how many half lives the particular nuclide has undergone? Five, na? Now we can also find out the fraction. This n0 is the original amount, nt is the number of nuclides present after n half lives. Yes, so we can also calculate the fraction of the nuclides remaining after time t is nt, sorry, look, nt by n0, this is the fraction of nuclides present, so that will be nt by n0. From the formula, you know, it is e to the power minus lambda t as well, and from here we have seen it is 1 by 2 to the power n. Okay, na? So what is nt by n0? This is the fraction of material remaining. It is not talking about how much has been decayed, it is the remaining portion. Fraction of materials remaining. N is the number of half lives. T by T half. So most of the time question are set from this particular. This slide is like very important slide. Let's move on. Let me know if it is done. Give it a try. A radioactive substance has a half-life of 5 hours. If you start with a sample of 80 grams, how much of the substance will remain after 15 hours? Look, mass of the sample can be directly correlated to number of nuclides. More number of nuclides means more is the mass. Do it quickly. You should not take more than 2 minutes for this question. Option B, 10 grams. Very good. Let's see whether we get it or not. So what is given to us? N0, it is 80 grams. Half life 5 hours. Time elapsed T is equals to 15 hours. The number of half life passed is N is equals to T upon T half. So 15 hours and this is 5 hours. So it is 3. So the fraction okay, the substance will remain, therefore the substance will remain after 15 hours is NT will be N0 divided by 2 to the power n. So N0 here 80 grams divided by 2 to the power 3, so 10. Option 2. Okay, let's do another problem. half-life of a radioisotope is 4 into 10 to the power 8 years. If there are 10 to the power 3 radioactive nuclei in a sample today, the number of such nuclei in the sample 4 into 10 to the power 9 years ago there. So you can see that here some radioactive isotopes can have half-lives in billion years, okay, in million years. So you can imagine from the time where all the dinosaurs got wiped out from the Earth's surface, if some radioactive isotopes or radioactive nuclei started to decay at that time, you can even today you can find their existence, because ideally it should take infinitely long time. So if the half-lives are much more greater for certain radioisotopes, so they will take a lot of time to decay. Very easy question, do it. D. So what we have here, T half 4 into 10 to the power 8 years. Therefore the number of half-lives T 4 into 10 to the power 9 years. So 4 into 10 to the power 9 divided by 4 into 10 to the power 8. So 10. 10 half-lives have passed and you got another 3. Nt n0 by 2 to the power n. So what we have to find out, the number of such nucleon sample where go. So before the decay, original amount we have to find out. So n0 it is, you need to find out, it is nt 2 to the power n. So nt is 10 to the power 3 and 2 to the power n. So 2 to the power 10. 2 to the power nt into 2 to the power 10. So 2 to the power 10 is 1024. Ajay. So other than half-life, there is another term called average life. What is this average life? Now, as I have already mentioned, that inside the nucleus there are hundreds and thousands of nuclei present. So we do not exactly know which atoms or which nuclei will decay first and which nuclei will decay later. So the atoms which disintegrates fast, they have very short life. The atoms which disintegrate later, they have very long life. So average life will be the sum of the lives of all atoms divided by total number of atoms. So you can imagine it in this way. Although we do not know which nuclide is decaying because of it is a statistical process, but we can predict something. We can say that, let's say, even if we do not know which nuclide are decaying, we can say that in the T1 time, dn1 number of nuclides are decaying. In T2 time, dn2 number of nuclides, T3 times. So you can say dn1 is a group of nuclides which takes T1 time to decay. dn2 is a number of group of nuclei which takes T2 time. dn3, this is a particular type of group of nuclei which takes T3 time. In this way, let's say Tn or dnn, or just you can write it in this way. So average life will have the formula now. Therefore, the average life T half, T bar, T average. This will be T1 dn1. Okay, dn1, each element is having lifetime T1. So sum of, if you want to calculate the sum of their life, so T1 d11, this is the total life of this dn1 group of atoms. So if you multiply T2 with dn2, this gives you the total life of this dn2 group of atoms, and T3 dn3, it gives you the total life of the dn3 group of atoms, and so on. Divided by total number of atoms. So it is, if you just sum it up, dn1, dn2, dn3, that will give you the total number of atoms. So it is sum over Tdn, we can write, divided by dn. Now for heavy nuclei, there are a huge number of nuclei. So this summation can be approximated to an integration. Okay, so you can write it T dn. Dn. Yeah. Now dn itself depend on t. N equals to n0 to the power minus t. So it is depending on t. So here the limit of t will be pushed. So the limit of t is, let's say you started from the 0 time, and how much it ideally takes to complete the decay? It is infinity. So t equals to 0 to infinity. dn, this is, let's say n0 number of nuclides are present initially, and ultimately how many numbers will be there? 0. So that is why this is written as integration t is equals to 0 to infinity t dn, and here you see n 0, so this is minus n0. Okay, there are n0 number of nuclides. Now what we have, dn is equals to d of nt actually. For the timing, let's avoid writing. N equals to number of nuclear pressure. N and nt is same here. Huh? So n is equals to n0 e to the power minus lambda t. We know it already. So this is minus lambda times n0 e to the power minus lambda t dt. So if you use this, then your t average will become 0 to infinity t dn, okay, and divided by minus lambda n0. Okay, so minus lambda n0, this is constant I'm keeping outside, t equals to 0 to infinity t dn. So t e to the power minus lambda t dt. So dn value we have put here, and divided by this minus n0. Can you write it? So this minus minus is absorbed. So lambda times 0 to infinity t to the power minus lambda t dt. Now you can take integration. Keep lambda outside and integration by parts. Take u t as u and e to the power minus lambda t as v. So u integration dv. So u integration of e to the power minus lambda t to the power minus lambda t divided by minus lambda. Now derivative of this is 1, integration minus minus plus 1 by lambda 0 to infinity e to the power minus t dt. So we are doing nothing but the integration by parts. So this is lambda, let's keep it minus t by lambda e to the power minus lambda t, and this will give you minus 1 upon lambda square e to the power minus lambda t. The limits will be from 0 to infinity. Here also the limits were from 0 to infinity. So if you put these limits, the first term contains t, so that first term will be 0, this term will survive. If you put t equals to infinity in the second term, the first term is 0, but when you put this 0 limit, it will minus minus plus, okay, 1 by lambda square, e to the power 0 is 1, so lambda into 1 by lambda square, that is 1 by lambda, है ना? So this will come out to be 1 upon lambda, and therefore we write that the average life t half, this is equals to 1 upon lambda. So we can relate it to the half-lives formula. Look, half-life, we know that t half. What is t half? T half is 0.693 by lambda. 1 by lambda is t average. So it is nothing but 0.693 times t average. Is it understood? Okay, so there is a term called activity. Do you know what is activity? Activity, do you know? Activity or strength. It is denoted by A. AT of a radioactive sample is defined as the rate of disintegration. Okay, and hence activity we can represent AT dNT by dt. So this is lambda times NT. So A is equals to lambda n, that is the relation. A is equals to lambda nt. You know it very well. What is this nt? Nt is the number of undecayed nuclei at time t, है ना? And lambda is decay constant. We have already defined probability of decay per unit time. So this is your activity. Now there are several units of activity. One of them being Curie. Curie is the name of Marie Curie. It is given on the memory of Marie Curie. Marie Curie is the one who discovered, who worked on this radioactivity. Okay. There are several units. The first one is Curie, in short CI. And 1 Curie is equals to 3.7 into 10 to the power 10 disintegration per second. So in 1 second, if 3 into 10 to 3.7 into 10 to the power 10 number of nuclei decays, we will say that the activity is 1 curie. So it's a big unit, right? So smaller units includes 1 millicurie, MCI. 1 millicurie will be 10 to the power minus 3 curie. 1 microcurie will be 10 to the power minus 6 curie. Okay, this is, let's keep it. Look, okay, this disintegration, one disintegration is 1 becquerel. So disintegration per second. So it is in short written as DPS, disintegration per second. This is called 1 becquerel, BQ. So this is nothing but 3.7 into 10 to the power 10 becquerel. Let's go for a problem. Consider a sample with an activity of A0 is equals to 6000 becquerel. If the sample has a half-life of 85 seconds, how much time will it take for the activity to decrease to 6 becquerel? Look, one thing I would like to tell you here, the way N behaves, A behaves in the same manner. So if you have a relation, let's say Nt is equals to N0 by 2 to the power n, activity, you can see activity is equals to lambda times Nt. So activity is proportional to Nt. Na? So the way you treat Nt, you can also treat At. Just a scaling factor, lambda is multiplied. Nothing more than that. Understood? So A0 will be termed as initial activity. Consider a sample with an activity of A0 equals to 6000 becquerel. If the sample has a lifetime half-life of 85 seconds, how much time will it take for the activity to decrease to 6 becquerel? So you are basically given A0 and At. This is your At, right? And half-life is also given, T half is given. So you have to find how much time will it take. So you have to find T. Could you do this? A0 is equals to 6000 becquerel. T half 85 seconds. T we need to find out, and AT 6 becquerel. No, so we know that NT is equals to N0 by 2 to the power n. So we can write AT equals to A0 by 2 to the power n. Can I write it? So 2 to the power n equals to A0 by AT. Initial activity is 6000 becquerel, AT is 6 becquerel, so it becomes 1000. So for what value of n it becomes 1000? If you take natural logarithm on both sides, so this is n ln 2 is equals to ln 1000. So from this we can get the number of half-lives. So we are basically determining how many half-lives have passed to decrease from 6000 becquerel to 6 becquerel. Therefore n becomes ln 1000 divided by ln 2. So the value of ln 1000 is 6.908, ln 2 is 0.693. So this gives you 9.97. Once we get the number of half-lives, we can easily calculate the time elapsed. T is equals to NT half. 9.97 into T half is given 85 seconds. So this is around 847 seconds. So 14.112 minutes. 14 minutes and 7 seconds, approximately 14 minutes. Is it clear? Tell me. Look, sometimes you may be given in terms of mass. Instead of giving you in terms of number, like instead of giving you n, you may be given in terms of mass. So how to correlate the relation between the activity and the mass of the radioactive substance? So we know the relation between the activity AT at any activity at any time t is equals to lambda times nt. We know it. So nt is the number of undecayed nuclei or number of decaying nuclei, you can also say. Now we know lambda is equals to 0.693 divided by T half. And what is NT? Can we write NT in terms of the mass? If you see, if there are, let's say in this way, n a number of N is Avogadro number. Okay, Avogadro's number. So if you have n number of atoms, then what you get? This is the molar mass, right? Molar mass, let's say m. So n number of atoms has a mass capital M. So nt number of atoms, how much? If they have, let's say, nt number of radioactive nuclei, if it has a mass, let's say m gram. Okay, let's say mass m, let's not specify unit. If nt number of nuclei has mass m gram, so what will be nt? If nt becomes Na, the mass becomes capital M. Okay, so Na number of atoms has mass m. So one atom has mass Na by m. There are nt number of atoms. So what we can write? Can we write this? Na by m, what does it show? Mass of n number of atoms is capital M. So Na by m gives you the mass of one atom. So Nt is equals to m times Na by m. Or you can imagine it in this way. Okay, m mass, we calculate the fraction. This is the fraction m mass, and if you multiply with the total number of atoms in 1 mole, it should give you Nt. Is it clear or not? Tell me. So here At will become 0.693 by T half. Capital M molar mass, small m is the mass of the substance. Mass of the radioactive substance, it is small m. M is equals to mass of 1 mole of atoms. I hope this is clear. So At becomes lambda times Nt. Lambda equals to 0.693 by T half. Nt is equals to small m by capital M times Na. So from here we can calculate the mass of the radioactive substance M. If you are given activity at any time T, so activity by 0.693 m times T half divided by the Avogadro's number. So using this formula you can calculate the mass of a radioactive sample. m is the mass in gram, capital M is the molar mass of the element, and Na is the Avogadro's number. What is Na? 6.023 into 10 to the power 23 per mole. I hope you all know. I hope you know all this. Let's solve a problem. Is it done? Harry, Ajay, Murli, Deep. Murli has not come today. Give it a try. 1 gram of radium is reduced by 2 milligram in 5 years by alpha decay. What is the approximate half-life of radium? 100 years, 950 years, 1730 years, 2620 years, 2680 years, sorry. Can you do this problem? Mass will also exponentially decay. So m will be equals to m0 e to the power minus lambda t. Lambda is ln2 by t half, 0.693 divided by t half. Initial mass is given to you 1 gram. Final mass reduced by 2 milligrams. So what is the present mass? 1 minus 2. 1 minus, here 2 in milligram. 2 milligram is 0.002 gram. Okay, so 0.002 gram. So this is 0.998 gram. This is after 5 years. So you can use this equation, m by m0 is equals to the power minus lambda t. So ln m by m0 e to the power, okay, m0 by m कर देते हैं ना, m0 by m is equals to lambda t. lambda is equals to 0.693 by T half. So 0.693 T by T half. What you have to find out? What is the approximate half-life of radium? So half-life is T half. T half is equals to 0.693 T divided by ln m0 by m. T is 5. Let's say we are putting it in years, so 5.693 divided by ln m0 is 1, m is 0.998. Approximately how much will it give? ln1 and 0.998, 0.0020, 1732.5 years. C. Look, ln1 is 0 minus ln 0.998. ln 0.998 is itself negative, so negative, negative, positive. Okay, so I think this is enough for today. We'll continue from here. Today we'll be starting with branching ratios and all, or maybe any other thing. So we'll start from here on the next day. Thank you very much guys for joining the session. I hope you find this session easy and interesting and useful. This is all for the session. Thank you very much once again. Bye bye, take care, have a great day.